Well, thank you for joining us this morning again. Steve Sanford, who was here last week introducing last week's lecture, could not be here. He's actually at NASA Glenn on travel, so he asked me to go ahead and introduce our next two presenters. As you know, if you were here last week, we had a great talk about the path to Mars and the Asteroid redirect mission by Pat Troutman and Dan Masnick. Well, now we're going to shift focus to our transportation architecture, looking at the Orion spacecraft and specifically the launch abort system. And joining us today, we have Kevin Rivers, who is the project manager for the Orion launch abort system. And the lead flight dynamics person is John Davison. They're going to give you an excellent talk over the next 50 minutes to an hour on that system. And hopefully some of those videos will work. We'll stay tuned. We'll see what happens. But I'm going to turn it over to Kevin and enjoy the presentation. Thank you.
Thank you for allowing me to spend some time with you guys today. I'm Kevin Rivers, and I do manage the launch abort system development for the Orion spacecraft, so I wanted to kind of talk you through that particular development. I think I need to begin, though, with a little bit of a history of human spaceflight, so I thought I would start from the very beginning with the Chinese. You guys may know the Chinese invented gunpowder, and as a result, fireworks. And they very quickly weaponized those fireworks into missiles. Those missiles were called fire arrows, and about 900 AD is when they first were used in warfare. And I can just imagine if you were used to a regular arrow coming sailing at you, if you had one that was rocket-powered coming at you, that would really ruin your day. But this technology advancement was enabled through the invention of the gunpowder and exploration through fireworks. So there are some early pioneers that need to be credited for spaceflight. Actually human spaceflight is something that's been in the mind of mankind for a very long time. As a matter of fact, as long as we've had recorded history, mankind has dreamed of traveling in space. Konstantin Tsiolkovsky was the first person to actually write about it. He has the first published works on space travel. And could be considered the father of space travel. Our very own Robert Goddard here in the United States actually invented and developed the liquid rocket. And then many of you are familiar with the father of rocket science, as Wernher von Braun is often referred to. He is a German scientist who actually came to the United States after World War II and became a U.S. citizen. The reason I bring all these folks up, and you can see in the photographs on the slide, the different dates of when they actually did these things. Tsiolkovsky actually at the turn of the century, as well as Goddard, and then von Braun actually led the development of the Saturn rocket for the Apollo program in the 60s. The required technologies for humans to fly in space really did not become available to us until the 50s, and that's why as soon as we had the technology and the capability, we certainly took advantage of it and moved quickly into space. The first U.S. program for human spaceflight, the Mercury program, ran from 1958 to 1963 and had some very specific goals. The first goal was to orbit a manned spacecraft around the Earth and return the occupant safely to the ground. To investigate our ability to function in space was also a very important goal. This was actually a very impressive program, and it was led here at Langley back in the 60s. And it's very impressive to me. They flew 6 crewed flights from 1961 to 1963, which I think was very impressive, and laid the groundwork for our understanding of how humans react to the space environment in that situation. So following, there are several, actually there are several very important things that occurred in the Mercury program. You guys are probably familiar with Alan Shepard. He was the first American into space in a suborbital flight in 1961. Astronaut John Glenn actually was the first American to orbit Earth. He did that on February 20th, 1962. And then after the conclusion of that very successful program and on a path to send humans to the moon, the Gemini program was conceived, and it actually operated from 1962 to 1966. It's a 4-year program. And the goals of that program were to develop key technologies necessary for humans to travel to the moon and back. There were some amazing firsts that occurred. Edward White was the first human to actually get outside of his vehicle in space, and he was the first spacewalker. He did that on June 3rd, 1965. And Walter Schirra, Thomas Stafford, Frank Borman, and Jim Lovell actually were the first people to accomplish a space rendezvous. They, on Gemini 6 and 7, actually rendezvoused those two vehicles, which was a critical technology that we needed to develop and demonstrate successfully in order to go to the moon. Following the Gemini program, the Apollo program, very successful and probably the most widely known human space program in history. That program was from 1963 through 1972. Obviously the purpose, as it was so eloquently expressed by President Kennedy, was to deliver humans safely to the moon and return them safely to Earth afterwards. And so there were 6 missions where crews landed on the surface of the moon. There were 3 other missions where crews orbited the moon. One of those 3 was, of course, the ill-fated Apollo 13 mission, which you may be very familiar with. Apollo 11 was actually the first mission where humans actually reached the surface of the moon, and Neil Armstrong actually was the first human to walk on the moon. So the Apollo program was extremely successful in our understanding of how humans interact with the environments that they're exposed to when they go extraplanetary, when they go to other planetary bodies. This is just a photograph of the lunar lander and the buggy, and I believe that's, where's Commander John Young? I think that might be him. I'm not real sure. So anyway, these guys did a lot of exciting things while they were on the surface of the moon. So following the successful Apollo program, NASA actually successfully executed the Apollo-Soyuz test project in 1975. This is where we docked our American-developed Apollo vehicle to the Russian-developed Soyuz vehicle. This was the first international partnership where 2 countries worked together to successfully execute a human spaceflight endeavor. And if you're interested, this is astronaut Don Slayton and cosmonaut Alexei Leonov. This is Slayton, that's Leonov. And they're greeting each other after the mating of the vehicles. So following that program, the Skylab was launched. The Skylab actually was a converted 3rd stage of the Apollo 1B. We put this vehicle up in orbit in May of 1973. There were 3 crews that crewed the vehicle. The longest any one crew stayed was almost 3 months before the vehicle deorbited and re-entered the Earth's atmosphere. This is Skylab 4 astronauts Gerald Carr and William Pogue. They're shown in the OWS, and I'd have no idea what an OWS is, but they're in it. But one of them's upside down. I don't know which one's upside down. Could be him. And then following that successful program, obviously the space shuttle was developed and flown. The first orbiter to fly was Columbia, and that was flown on April 12th of 1981. Commander John Young and Robert Crippen flew that vehicle successfully to orbit and back. This is the first spacecraft that was capable of routinely launching and returning from orbit, and it was the first reusable spacecraft to be developed. The space shuttle had about a 40,000-pound payload capability, and the marvelous thing about this machine is not necessarily that it could take 40,000 pounds to orbit. A lot of vehicles could do that. It's that it can bring 40,000 pounds back, which is very amazing. So that program ran through 2011, and the space station, actually on orbit today, that program started in 1998, and the vehicle is in its full configuration currently in orbit above the Earth. The first crew actually arrived to the space station in 2000. So that's kind of a history of where we've been. I'll talk a little bit now about where we're headed. Where we've been, obviously, in the early 70s, we put humans on the moon, which was an amazing feat. But most recently, we've spent most of our time in low Earth orbit. And I show this chart, and I know that you guys last week, if you were here, you actually heard this story a little bit. Our current systems are Earth dependent, and low Earth orbit is only 200 miles away. That's a trip to DC. So it's, although in a much bigger vehicle. So to put things in perspective, the moon is 240,000 miles away, and Mars is 35,000 miles away. Quite a big difference in distances. And so as we move towards that mission and try to realize the opportunity of humans exploring Mars, we have to develop new systems to do that. So we need to move from these Earth-reliant systems that we currently have and out. When we do explore Mars in the 2030s, we're going to need to have systems that are planetary independent in order to explore Mars and its moons successfully. So what we're doing now is we're in that middle proving ground. So we're trying to prove out some technologies and capabilities that allow us to do that. The Orion vehicle is obviously the crew vehicle that we're going to use to do that. And flying some of these intermediate missions, like a mission to explore an asteroid, are opportunities for us, just as we did in the old days with the Gemini program, just where we can prove out the technologies that we'll need in order to successfully explore Mars. So this is the rocket that we're going to fly on. It's currently under development by the Marshall Space Flight Center. This is the Space Launch System, the SLS, if you will. I like to think it's an elegant combination of the shuttle and Saturn. So it used the shuttle parts and it was painted like the Saturn. That joke didn't go over too good, but anyway, maybe you'll get it if you can see this. So this is the SLS. The core stage is the primary vehicle. It's actually propelled by the RS-25 engines. These are the engines that propelled the shuttle. These are the shuttle main engines. And then it also has solid rocket boosters to add thrust in the initial stages of flight. The vehicle's 321 feet long. This actually shows the configuration with the Orion spacecraft atop it. And the thrust of this vehicle at liftoff is a little over 8 million pounds. So it's 8.4 million pounds of thrust whenever it lifts off. Just to compare the SLS vehicle to other vehicles that have existed or do exist, I've shown the payload capability. Mass is in blue, volume is in orange, and you can see here, well, maybe my joke makes sense now. We decided to go back to the Apollo Saturn paint scheme. But anyway, the first SLS that we will field will have a little bit less capability than the Saturn V, maybe 2/3 of the capability for payload, but ultimately we'll be able to do more than we could do with the Saturn vehicle whenever we implement the second iteration of the version, or the payload carrying version of that vehicle. So this is a schematic showing the various components of the Orion vehicle. So I'm going to move in and talk a little bit about our human vehicle, the crewed vehicle. This is the launch abort system. This is the system that John and I work on, and John will give you a lot of great details on that system in a little bit. The crew module looks a lot like an Apollo capsule. It's a conical vehicle and re-enters the Earth's atmosphere on a ballistic trajectory. And then that vehicle is supported during its space travel by the service module, which provides all of the power and utilities and things that are needed by the crew. The vehicle can support crew members for short or long duration space flights, flights currently up to 21 days. And it supports a crew of anywhere from 2 to 4 astronauts. You might ask, how is that different from the Apollo vehicle? This schematic shows actually the Orion is quite a bit bigger than the Apollo vehicle. The Apollo vehicle could hold a crew of 3 with a habitable volume of about 218 cubic feet. The Orion vehicle can hold a crew of 4, and if we were going to low Earth orbit, we could actually carry 6 crew members with a habitable volume of about 350 cubic feet, so almost twice as big inside as the Apollo vehicle. So I just want to show you a little video here of the of the Orion. This will highlight the vehicle and its development. So that's Orion in 30 seconds.
Pretty good.
Yeah, we like our music. So anyway, the Orion vehicle is quite a marvel, and as you could see through that video, developing a vehicle like this is a very complicated activity and actually takes quite a few years. This kind of shows some of the developments that we've been involved in to date. And I apologize that all these pictures are so small. But you can just see by this host of activity early, since we started back in 2005 until today, a lot of development testing has occurred, including the Pad Abort 1 flight test, which is this demonstration of the launch abort system. And that was in 2010 when we flew that. We're gearing up now for our first space test flight, which is Exploration Flight Test 1. That's where the crew vehicle is actually going to go into space. And then ultimately we will fly a couple of other test flights as we certify the system for human spaceflight, which is not an easy endeavor. And then ultimately we'll fly our first crewed mission in 2021, which is the EM2 mission. So let me tell you a little bit about some of the details of this as we move forward. So this is the EFT-1 mission. We're going to fly 2 orbits around the Earth. On the second orbit, we're going to swing out to about 3,600 miles, which is the reason we're doing that is so that we can actually re-enter the Earth's atmosphere at near lunar re-entry speeds. We can't quite get lunar re-entry speeds, but we want to get as close as we can. And obviously, we're doing this test to demonstrate some of those critical systems like the heat shield, the thermal protection system, the entry guidance and navigation and control system, and then finally the parachute landing recovery system that's required. So this test will demonstrate all of those high-risk areas, which will, we believe, put us pretty far ahead of the curve on development. So this is just a photograph of some of the hardware for that mission. It's going to fly in December 4th out of Cape Canaveral. This picture is, I'm sorry to say, very dated. Actually, the vehicle is completely closed out at this point, and they're fueling the crew module right now in preparation for integrating the launch abort system on top of it. But I have a video, and this is a video that may or may not work, so let's see if it works. This is the EFT-1 mission. So we're flying on top of a Delta IV Heavy for this mission. So this just shows that we're going to orbit the Earth twice. On the second go-around, we're going to slingshot out, get the vehicle up to near lunar re-entry speeds, and then as we return, the crew vehicle will separate from the service module and re-enter. So that's that slingshot maneuver. And we actually are going to use this upper stage to accelerate once we're coming back. We're not just going to throw it out there and let it fall back. We're actually going to accelerate it back. This is what the view would look like if you were crazy enough to ride it. There we go. Now, so there's the crew module separating from the service module and then re-entering the Earth's atmosphere. And I apologize, I don't off the top of my head know what the heating rates are for this vehicle when it re-enters, but it is significantly higher than a vehicle experiences when it re-enters low Earth orbit. And then ultimately, parachutes will come out and the vehicle will splash down in the Pacific Ocean. So I do want to point out the recovery of this vehicle is being performed in conjunction or in cooperation with the Navy. And so the things that we do are sometimes very complicated organizationally because we do have to work across multiple agencies to get things done. So that's an example of that. So that's the EFT-1 as it splashes into the Pacific Ocean. Yes, it actually will start its entry at 20,000 miles per hour. And we believe it'll splash down somewhere around 1830 miles per hour. Is that about right, John? So quite a bit of deceleration there. Feet per second, I'm sorry, thank you. So that's the Orion. The other two missions that we're going to fly, the first one obviously is to demonstrate all of the deep space systems that we'll need to successfully fly crew. That's EM1. We're actually going to fly that vehicle around the moon. That mission is actually maturing a little bit now. We've actually probably made a change, or will make a change in the near future, to fly actually to a Lagrange point, which if you don't know what a Lagrange point is, a Lagrange point, there are actually three. That's a point where all of the gravity influences are negated by each other. So it's a point where if you actually went there, you would require no energy to stay there. So there's a point between the Earth and the Moon, there's a point on the other side of the Moon, and there's also a point on the other side of the Sun where the Sun's, Earth's, and Moon's gravity all equalize each other. They're called Lagrange points. We're actually going to fly to L3, which is the Lagrange point out behind the Moon. We're not going to go and stay there, we're just going to go and do a flyby. Because we believe that our next mission is actually going to be to fly to a Lagrange point and allow a crew to operate from that point. And then our first crewed flight, EM2, obviously this shows schematically that we're going to put the crew in orbit around the Moon. For those of you who are familiar with the Apollo program, that was actually the first crewed mission for Apollo, where they put the crew in orbit around the Moon, and they did so on Christmas Eve. So, what a Christmas present. So I mentioned that we have to, it's very complicated to do this technically, but it's also very complicated to do this because we have to partner and collaborate with multiple entities. Actually, our NASA team, you can see here that all of our NASA centers are involved in this mission. Obviously, Johnson Space Center is where the program is led. Langley is where we're doing the launch abort system, et cetera. But a lot of people are contributing across the country to this program. So Langley actually is contributing in multiple areas, and this kind of captures a multitude of those areas where Langley is contributing to the development of Orion. And I'd like to go through this real briefly, if you guys don't mind. Obviously, Langley has wind tunnels, and we do a lot of aerosciences work, so we're doing a lot of wind tunnel testing. We also have a facility which you can see from pretty much anywhere on the peninsula. It's called the gantry, where we do drop testing. So that we can understand the dynamics of and loads associated with the vehicle when it enters the water. And we have a group that does the trajectory analysis for all of these entry simulations so that they can understand the heating environment, et cetera, et cetera. We are developing the launch abort system, which includes doing the guidance and control and design, as well as the performance predictions for the launch abort system, which is what Dr. Davidson does for us. And we've obviously done computational fluid dynamics studies, which is basically wind tunnels on the computer, as well as investigating some navigation systems and the like. So this is, I think I'm going to show you a video next. Yeah, this is a water drop test that was performed at the gantry that I mentioned. So we've actually performed several of these tests. This was a pretty extreme impact, and that's why the vehicle actually rolled over. Don't worry, though, there is a righting system on the vehicle. It's not on this test article, but the actual vehicle actually has a system that allows it to flip back over top up. So this is just a little bit more detailed view of the vehicle as it impacts the water. So these entry loads, when it impacts the water, actually drive the size of a lot of the structure and the secondary structure, and so it's very important that we understand these loads. They're hard to predict, and that's why we do test, so that we can minimize the mass of the vehicle to the greatest extent possible. So Langley also was very involved in the development of the heat shield. This is actually a photograph of the EFT-1 heat shield. This is at Textron Industries in Boston, Mass. This heat shield, actually, the material is Avcoat material. It's a derivative of the material that was used on the Apollo program. And it was quite difficult to develop, actually, because we lost the recipe. And actually, yeah. Actually took us about 3 years to reconstitute the material and demonstrate it successfully in ground testing. And Langley was in the middle, very actively involved in that activity in collaboration with Johnson Space Center and with the Ames Research Center out in California. And then the launch abort system, I mentioned that we lead that here at Langley. The reason we lead it at Langley is because Langley has a breadth of skill sets that's probably unique across the agency, in that we have the guidance, navigation, and control folks, the flight dynamics folks like Dr. Davidson. We also have the structures folks and the loads and dynamics folks. So we can take a very complicated vehicle like the launch abort vehicle and analyze it through all different phases of flight. And so we have had that responsibility since 2005 and successfully demonstrated the abort system in Pad Abort 1, which was in 2010. A little bit about the launch abort system. Obviously, it kind of makes Orion unique and when compared to current and existing systems or systems that we recently fielded, like the Space Shuttle, in that we can actually recover the crew if we have a launch accident and safely return them to Earth. That makes our system substantially safer than the shuttle was, and actually significantly safer than the Apollo, even though it had a launch escape system. This system, developed back in the 1960s, actually was very limited in its capabilities. There were actually many phases of flight where it couldn't be used, and our launch abort system is designed to be operable from the pad all the way up to 300,000 feet through all phases of flight and all speeds. And what allows us to do that is we actually have implemented an active flight control system. And actually, I guess at this time, John, if you want to come up, I'll let you describe that system and talk a little bit more about the launch abort system.
Okay, thank you.
So, thank you all.
Yeah, so the rest of the talk is just going to focus on the launch abort system. As Kevin said, we've done a lot of work at Langley to support the design and development and also analyze the performance of the launch abort system. So as Kevin said, the launch abort system provides the capability to do aborts from the pad all the way up to approximately 300,000 feet. Above that, you can use the service module to do aborts. That's because you're essentially outside the atmosphere at that point and don't have like atmospheric drag and things like that to overcome. As we got just here a graphic of the launch abort system and Orion on an SLS, and then just a graphic of what that abort system, the big abort motor firing, would look like. As Kevin said, similar system similar in appearance on Apollo. They had a tower escape system, but the Orion system uses what's called active flight control, and that's a big difference between us and Apollo. Apollo was a passive system, and so what the active flight control does for you, it allows us to actually steer the trajectory and also control the attitude of the vehicle during the abort. And that capability significantly, as Kevin said, improves the crew safety over a passive type system. So this is just a graphic showing an overview of what the abort sequence would look like. Should there be a problem on the launch vehicle, that you give sensors on the launch vehicle and they tell you there's a problem with an engine or you're off course or something like that, you would detect the abort and you would have a signal that you need to do the abort, and the abort sequence would look like this. First, when you start the abort, there's a big abort motor that fires to quickly pull you away from any trouble that might be occurring on the launch vehicle. And at the same time, there's this called an attitude control motor. So a motor that produces thrust and forces to steer your trajectory and keep you pointed nose forward. The abort motor burns only for about 4 or 5 seconds, but produces like a peak of 400,000 pounds of thrust. That gives you about 12, 13 Gs of acceleration. That's to get you away quickly from any problem on the launch vehicle. You then coast for a while under control with an attitude control motor, keeping you in a nice, stable, nose-forward condition, because you're probably going very fast coming off the launch vehicle. You need to slow down, because what we need to do is we need to turn around, because the parachutes we use the same parachutes that are on the top of the crew module. So you need to turn around, slow down, turn around in a maneuver we call a reorientation maneuver to heat shield forward, and that's done again using the attitude control motor. So you need to get it turned around and in a steady condition heat shield forward, and that's another benefit of this attitude control motor, that it does that for us with the active flight control. You then, once you get steady, you fire a jettison motor, pulls the launch abort system off the crew module, and then there's a little cover that's called the forward bay that comes off, that's a cover on top of the parachutes. That comes off, and you go through the regular parachute sequence down to the water. As Kevin said, we're designed to do water landing similar to Apollo. Now, so this provides the abort capability up to 300,000 feet, and as you might imagine, this happens pretty quickly. So right now, when you're at high altitude, the time from abort initiation, from leaving the launch vehicle all the way to LAS jettison, is on the order of 25 to 30 seconds for this whole sequence of events. When you're doing like a pad abort, as you might imagine, it has to happen a lot faster because you're near the ground. Because you need to get up, out over the water, turned around, and they got to get the system off and parachutes open so you have enough time for the whole parachute sequence. As you saw in the video, there's a number of parachutes that open. They have to be, of course, fully open to get you down to the water safely. So when you're doing a pad abort, it happens more on the order of 15 to 20 seconds. What I have here is an animation. It's an older animation, but it was of an early concept for an abort test. Kevin talked about we've got an Ascent abort test coming up in the 2017-2018 timeframe. So this is an animation showing about what that would look like. And I apologize, this is using an older launch vehicle that we're not using anymore. So this is not going to be the launch vehicle that's used in the Ascent abort test, but it's a good animation video that shows you what the abort would look like.
We have separation. Stage 2 RTU and all the GVC pressures are nominal.
So we fire. He fires the abort motor to get you away. The attitude control motor is firing to keep you on course.
Vehicle avionics and booster power
There
systems are nominal.
does a controlled reorientation to get you back to this heat shield forward condition. Of course, then jettison. The abort system, that's that cover on top called the forward bay cover. And then you go essentially into the standard entry sequence.
Mr. Indy Delta's on 36. As written, flight max 37.
There are drogue parachutes that come out when you're at higher altitude to stabilize the capsule before the main parachutes.
Avionics parameters
Then
remain.
cut those away, and then go through the main parachute sequence, which it fires out small parachutes called pilots that pull out the main parachutes. And just interesting, they called reefed, so they don't open all at once to reduce the stress on the parachutes, so they go through a sequence of opening smaller and then slowly open larger. It's called reefing. Yes, sir?
During the abort sequence,
Finding all operations on 3-4. Copy that, thanks.
reversing itself has a problem in some way. Is there enough fuel to try that reverse again?
It's a solid rocket motor, so it has a fixed amount of burn time. But right now, the control system, because we have this active control system, it's all computer controlled and it continually senses your attitudes. The way the active control system works, the computer's in the crew module that sends signals up, that sense your attitude, make steering commands, send those up to this control motor, which we'll talk about, and that provides the turning. So the computer on board is constantly determining your attitude to get you on the right trajectory. So it's not controlled by the crew. Yes, sir? Sir.
What assures that the capsule is going to land in water wherever it aborts? Whatever.
Oh, okay. That you land in the water? Yes, sir. The trajectory we have right now for like going to a lunar orbit, if you, going to an orbit first that would then take you onto a lunar orbit, is out over the Atlantic Ocean. And so the launch abort system, the farthest that you would abort going out over initially is 300,000 feet in the orbit, puts you out about a third of the way or so out into the Atlantic. So higher than that, you do a service module abort, which then, they actually can target where you're high enough up that you can actually target where you re-enter. So you would then probably skip back over, go high enough up to re-enter like into the Pacific. There's an inertial measurement unit in the crew module to give you information about your attitude and accelerations, positions, things like that. Yep.
Will they be using re-entry tile to protect the heat? And if you do lose tile, how do you prevent that becoming a disaster after you're into the orbit?
Yes, sir. Like Kevin showed earlier, we're using a system similar to Apollo, which was Avcoat, the Avcoat design. It's a monolithic, so there are no tiles. It's single piece.
It'll be a single piece.
Yes, sir.
If during launch something happens to whatever part of that computer that controls the abort system, is there a backup computer?
Oh, yes, sir. We've got redundant, similar Apollo and the shuttle. Most commercial and high-performance aircraft have redundant computer systems. Sir, I believe he was, yes, sir?
Wouldn't you lose consciousness at 12 or 13 seconds?
Well, that's why it's, the system is all computer controlled, so it does not require crew intervention. So that's why we made it computer controlled. Should the crew, I guess I'm not in the human factors area, but I believe, yeah, the humans can take, short periods of high Gs and still remain conscious, but you can't sustain high Gs for long periods of time without, and still remain conscious. So we just have a peak of on the order of 10 to 12 Gs for a very small period of time. But as I said, it's computer controlled, so it doesn't require crew intervention to do, anything during the abort sequence. Yes, ma'am?
That answered actually my question, because when we brought back Apollo 13, it was the interaction between mission control and the astronauts in the capsule that made it the safe return. And I was going to ask basically the same question.
Yeah, that's an advantage of our system, at least the abort system over Apollo, is you're right, there were portions of the abort with Apollo, especially high altitude, where actually required crew intervention, like to do that reorientation to get to a steady heat shield. The crew had to take command and actually fly it back to heat shield forward. And our system is all computer controlled with this active control system for the abort system. Yes, sir?
This is probably more for Kevin, but
Okay.
I suppose that these flights create an awful lot of heavy, big debris. What happens to it? Lots of stuff gets peeled off. Where does it go? What happens to it?
So actually, that is a really good question. For any launch that we do, we actually, in order to satisfy the requirements of the range, the Air Force that controls that space, is we have to demonstrate that we are not going to leave what is referred to as a water hazard, meaning we're not going to leave something large floating around on the surface of the ocean that a ship could actually impact and be damaged by. So we actually do very complicated analyses, and for the launch abort system for this upcoming EFT-1 mission, actually, we here at Langley did the water impact analysis. John actually provided the boundary conditions, the initial conditions for our structures analysts to do those analyses to predict how this large piece of hardware behaves whenever it impacts the water. So I don't have that simulation. It's actually very interesting to look at it. But essentially, this 30-foot tower actually is compressed into a very small 5 or 6 foot tall column of metal whenever it impacts the water, and actually sinks to the ocean floor very quickly. So.
Yes, sir?
If I was interested in the composition, history, development, and evolution of the propellant systems from the Saturn on, i.e. the propellant fuels, both solid and liquid, where would you direct me to go?
Marshall Space Flight Center.
So, okay, let me see if I can, I'll see if I can help answer that. Yeah, you could certainly get that information in Huntsville, Alabama. So there is a lot of information about the historical systems and materials that were used for the liquid fuels. Obviously, we, NASA, primarily use hydrogen fuel, and we have to carry oxygen with us, so we have a lot of liquid oxygen that goes along with us. Some of the other rockets that are out there, for instance, you guys may see in the news SpaceX and their Falcon rocket, and they actually use kerosene as their fuel. And a lot of, like the Atlas V uses kerosene, the Delta IV Heavy that we're going to fly on in December uses hydrogen. Now, when you talk about the solid propellants, that's a little bit more, sorry, I can't help you, because those materials are used in missile systems and weapon systems by our military, and their composition is tightly held and controlled information. Now, you may be able to find out some information about older systems, like the solid material, propellant materials that were used in the launch escape system for Apollo. That information may actually be out in the public, but the materials that we use, we could not tell you the composition. I can tell you that the solid fuel is like an elastomer. It's like a rubber-ish material. I can tell you that the solid propellant contains the fuel and the oxidizer in a very precisely controlled mix. So we don't just have, like hydrogen and oxygen that's all mixed up together. So then when it burns, we have to supply our own oxygen to keep the fire going, so to speak. And I can tell you that our propellant systems, our solid propellants, are actually based on, for instance, the jettison motor propellant is designed to be a very clean propellant. The reason it's designed to be clean is because we use that motor for every mission, and we don't want to fire up that jettison motor and contaminate the star trackers that are on the surface of the crew module or the windows or any of those kinds of things. So that propellant actually is designed to burn very clean without any particulates or aluminum particles and things like that flying out here and there. And I can tell you that most solid propellant systems are, the fuel is primarily aluminum, but there's lots of other magic fairy dust in there that we can't talk about.
Acid permanganate and hydrogen peroxide, use it all anymore for separation or anything? I know that's old stuff.
No, primarily the separation maneuvers are done with solid rocket.
Thank you.
Yeah, thanks.
Yes.
Going back to the Orion entering into the atmosphere, you said that the capsule is going to accelerate. Did I understand that right on entry?
Yeah, I apologize. If I said that, I misspoke. It's not accelerating as it enters the atmosphere. It is accelerated to a very high velocity before entering the atmosphere. So we accelerated up to 20,000 miles per hour so that we can simulate the speed that it would enter the atmosphere at if it were returning from the moon, for instance. So it's not actually accelerating when it enters the atmosphere. It's actually decelerating.
Yeah. Yes.
Perhaps I did not understand the answer that you gave the gentleman at the balcony.
Yes.
To an earlier question, but that service vehicle is a considerable size. Does it completely disintegrate since it has no heat shield when it comes in, or does it fall as it is into the sea in a single piece? I
Yeah.
want to be able to show my grade.
So I'm a little bit out of my technical area of expertise, but there have not been large segments of these vehicles to impact the Earth whenever they re-enter. For the most part, they are consumed in the atmosphere. If you recall, the shuttle external tank is a very large structure. That vehicle re-entered and burned up in the atmosphere mostly. I mean, there were some small parts that actually did make it to the surface of the Atlantic, but they were very small. So for the most part, no, it's not a large structure that impacts.
And just during a nominal entry, there are maneuvers to separate the crew and the service module, and the trajectories are chosen so that when the service module hits the water first and it's in a cleared corridor as you're landing, then the crew module lands closer to California.
Could you distinguish between the SpaceX rocket that's been in the New fleet and Orion?
Okay, a big difference between the commercial crew and Orion is commercial crew is just focused on low Earth orbit. Remember the graphic Kevin showed you? Taking crews up to the International Space Station and also cargo up to the International Space Station. And the International Space Station is in a relatively low orbit. You said like 100 miles or so? 200 miles?
200 miles.
200 miles or so in their orbit, where the Orion is being designed for going beyond low Earth orbit, going out missions to return to the moon, go out to near-Earth asteroids, missions like that. Yes, sir?
How precisely is the point of re-entry determinable so that a service ship is nearby, not right there?
Yes, sir. So right now our nominal entry from a mission is off the coast of California, so close to where we have some large naval bases that can send a ship. But yeah, there is uncertainty due to the winds and things like that that are taken into account, so you get essentially like a landing ellipse almost. It is steered as it enters to try and reduce the variability of the in the landing point, but you try and reduce that, and you do analysis. There's a number of analyses that are done on the day of the entry to try and more pinpoint where the landing is.
So what sort of range is available?
I'm not familiar. I'm in the launch abort office, so I've seen analysis, a lot of the analysis done by the entry people, but I'm not that familiar with it. Questions? Okay, so I think we've had some great questions here. Already gone through some of the issues of why it's hard here, but I've summarized some of the key issues. As you might expect, this is a difficult technical problem, talking about the launch abort system, designing the abort trajectories. One of the big issues is, like we talked about, we have to have controlled flight flying nose forward. We then have to slow down and then do this reorientation maneuver and get into a steady condition heat shield forward. So the reason this attitude control motor and active control allows us to do that, because as you might imagine, if you've got an out-of-control launch vehicle or an explosion, you might have a severe initial condition, a large rate or angle of attack side slip, that the system can take that out and get you back steered on an appropriate trajectory and control your attitude. Also, as I talked about, getting steady heat shield forward is very important, both to get a clean separation of the tower and a good condition for your parachutes to deploy during entry. And as if you think about it, we have to design here a system that can both fly well forward and backward. And you really can't say that for any aircraft you've ever flown on. They're only really designed to fly forward. So we almost have twice the problem here as far as the control design. We also have to operate over a very large altitude and speed regime, going all the way, as we've talked about, from the pad up to 300,000 feet, so through most of the atmosphere, and there's a large amount of atmospheric change. The properties and density, the temperature of the atmosphere change a lot over that altitude range. And also that takes us a speed range, of course, from Mach 0, which is, you're not moving on the pad, all the way up to hypersonic, Mach 9, 9 times the speed of sound, up at the 300,000 feet at the top of our operating condition. Also, this transonic region, the region what we refer to as around Mach 1, actually is a very challenging region to model and test. Here's just an example of what some of the issues here. This is, like Kevin talked about, computerized wind tunnel CFD visualization. You see that these are plumes from the control motor, plumes from the Abort motor, and there's very complex interaction both with the flow field, because you're moving very fast and the wind is blowing those plumes back, and also interaction between the plumes and the geometry of the body. And that makes it very difficult to get good computer aero database models that we can use in our computer simulations. So we've done a lot of work at Langley in some of the big wind tunnels to support development of the aero database. It's been critical to the program. So here's just an example of one of the launch abort system models in the NTF in one of our 14 by 22 wind tunnels, and also here in the vertical spin tunnel, a tunnel that allows you to observe dynamic motions of the vehicle. Quickly, some of the parts of the launch abort system. As Kevin said, the tower itself is approximately 30 feet tall, but if you include the fairing, the whole thing's about 50 feet. 3 feet diameter at the tower, and 17 feet to clear the complete crew module at the bottom here of the fairing. We've got, from the top, got a nose cone. We've got this attitude control motor, which is actually this motor that enables the active flight control for steering. It's the motor that produces pitch and yaw moments to give us the steering of our trajectory and controlling our attitude. Really enables the active flight control. Jettison motor, which, as we talked about, at the end of the abort and on a nominal mission, that's a smaller solid rocket motor that'll pull the launch abort system away from the crew module. The abort motor is this really big motor here, all the way from the nozzles all the way down here, about to down here. It's called reverse flow. The nozzles are actually at the top, is what that means, and the propellant is below. So it carries enough thrust here to quickly pull the crew module away if problems happen during the launch. And as a peak, we talked about 400,000 pounds of thrust, which is on the order of about 10 to 13 Gs of acceleration. And also then at the bottom, we also have this what's called the boost protective cover, or we call it the ogive fairing. And it's a fairing that protects the crew module during a nominal launch. It just protects the crew module from any aerodynamic loads and heating, also reduces the drag of the launch vehicle a little bit. But during an abort, also it protects the crew module from the abort motor plumes as they fire. So I don't have time to talk about all those motors. All those motors, as Kevin said, are solid rocket motors and were designed especially for the launch abort system. So I'm only going to talk here about one, which I think is the most amazing of our motors, developed by ATK in Elkton, and it's this attitude control motor. So what it actually is a motor that, as we talked about, gets commands from the crew module, go up to this motor, and it produces thrust, pitch, and yaw moments, which is thrusting in both the longitudinal and lateral planes to actually allow us to initially steer the vehicle and control the attitude. It's actually what's called a controllable solid rocket motor, so you can actually control where the thrust output goes, which allows us to do the steering, and it can exert up to 7,000 pounds of steering force to the vehicle. So here I've got an animation of actual video of a ground test that was done. We did a number of ground tests before the actual pad abort flight test for development of the motor. And so just walking, I saw this motor before the test, and it doesn't look very impressive. It looks like just a big, oil can, oil drum. But here, if you see it firing, it's quite impressive. It's going through a set of pre-programmed maneuvers here just to show how you could steer the thrust to any direction you want. No, it's pitch and yaw moments. Okay, so let's talk about pad abort 1. Kevin talked about we had a successful flight test, first flight test of Project Orion, successfully conducted May 6, 2010, out at the White Sands Missile Range. That was the same location, same area that was used for the early Apollo tests. It was the first test of an active launch abort system. And just some fun facts here. It was 135 seconds flight from launch to touchdown. This was an earlier motor that produced more acceleration, and it was a little warmer day, so we actually got to be 15 Gs of peak acceleration. Of course, there was no crew. This was just a test flight. a max velocity of 539 miles per hour, and we got a max altitude of 1.2 Gs. And of course, here with the NASA talk, I had to include some technical data here to show you. So what our group does here in the Launch Abort system is we run big computer simulation models to actually try and predict what the trajectory looks like, where you're going to go before the flight. So you can answer questions like, how far am I going to go? How fast am I going to go? Where am I going to land? Am I going to land safely? Things like that we can do with our computer models. So this is just an example here of altitude versus time plot. So you imagine how high up you're going with time. And what we did before the flight test is, it's very difficult to predict the exact winds of the day and the exact temperature. There might be some variation in the weight of your vehicle. So we run our computer simulations over and over again, changing these things a lot. Do a run at one temperature and one set of winds. Do another run at another temperature, another weight, another set of winds. Change the aerodynamics, things like that, and do a lot of computer runs. So this is like about 2,000 computer runs. So we're varying a lot of things that we think might vary on that day of flight. And that gives us a bound on what we think the predicted performance should be. And then we have like what we think is the nominal condition we're going to fly at. So that's what the blue is here. The light blue are all our varying simulations, varying a whole bunch of things, trying to predict the performance before the flight. And the blue, darker blue here is what, if everything's nominal the way we think it is, based on our information, best understanding of the winds, that's what we think the trajectory was. So overplotted here in red are the actual flight test results we got after the flight, just to show you. So one, we're pretty close here to the actual prediction of the nominal performance. And you can see here we're well within the band of given the variations we thought could happen on that day. So that's just an example of some of the analysis we do. So of course we do this, over and over and over again a lot because, as the design changes, we continually update our computer models. Some of those wind tunnel tests that we talked about generate force and moment information, and we use that in our wind tunnel models, use motor information and all that. Okay, so coming up next, I've got a really nice, it's about a 3-minute video on the Abort 1 flight test. It's a summary. First includes some of the test firings of some of the different motors. You'll see the attitude control motor again, the abort motor test firing, those are done on the ground, the jettison motor firing, and then a compilation of some of the videos that were taken during the actual PA-1 flight test to show you what that looked like. That's the jettison motor. That's the trailer we use to put all the parts together.
So I believe that's it for us. Just a slide to wrap it up, and then if we have time, which I do believe we have a few minutes, we'll take some more questions. So just in conclusion, the Orion multi-purpose crew vehicle will serve as the next generation of space exploration vehicles. It's being worked by multiple NASA centers, and our prime contractor is Lockheed Martin. The launch abort system is being designed to significantly improve the safety of this vehicle by allowing us to recover the crew in the event of an emergency and deliver them safely to the ground. And then, as John mentioned earlier, there are a number of test flights that we still have planned, EM1, the Ascent Abort Flight Test 2, and the final crewed flight, EM2, which is in 2021. So.
Tell us more about the December 4th test that you mentioned.
Yes. So certainly, and I'll get to your question, sir. Briefly, Exploration Flight Test 1 is going to fly December 4th, probably about 8 a.m. in the morning out of Cape Canaveral. We're flying on top of a Delta IV Heavy. We're going to do 2 orbits, accelerate the vehicle to 20,000 miles per hour, and then re-enter the Earth's atmosphere at that speed, which is just slightly below the speed that we would re-enter from if we were returning from the moon. And our primary purpose for doing that test is to demonstrate the heat shield, which is a very important and critical system, as well as demonstrate the flight control and the parachute or landing recovery systems. So it's a very important test for us to buy down what we believe are some of our highest risk. We talk a lot about risk in the spaceflight industry. And so we want to make sure that we understand our risk and that we address them appropriately, and so that's why we're doing this test. Thank you. Sir?
You indicated that instead of tiles, you have a covering that you have previously either used or tested as a one-piece shroud, you might say. After it expands through whatever's going through that heats it up, then you have to reverse things and turn it around and do it and cool it down. I don't know what you do, but is there a likelihood then that there's going to be any lack of complete contact when it recovers from the heat?
So if I could explain a little bit more about the thermal protection material. It's obviously we call it AVCoat. It's fabricated by Textron Industries in Boston. It is the system that was, it's a reformulation of the system that was used on the Apollo vehicle. And if you ever find yourself at the Air and Space Center downtown Hampton, there actually is an Apollo vehicle there, and you can actually go look at the surface of the vehicle and see that material. It's actually, if you're familiar with honeycomb structure, it's actually a honeycomb that's bonded onto the metal surface of the vehicle, and they fill each little cell of the honeycomb material up with this AVCoat ablative material. So it actually, the way that it's a passive system, if you will, the way that it keeps the heat managed is through ablation. So actually, it's charring, it's slowly burning away as it's re-entering, and actually, we size it to a certain thickness, knowing that it's going to burn away a certain amount, and we want to make sure that we have enough insulation whenever we get to that point, that we don't overheat the substructure below it. So that's kind of how it operates. Now, the back shell, the conical section of the vehicle, actually is protected with tiles that are similar to the tiles that were used on the space shuttle. And to hopefully preemptively address a question that might come up, I believe if those tiles were lost during flight, it would probably not be a catastrophic issue because it's on the back surface of the vehicle. So we might have some local heating issues, but I don't think we'd have a catastrophic failure. So does that answer your question? Okay, thank you. Yes, sir.
If failing happens just after leaving the launch pad, you wouldn't even notice within the atmosphere, or do you actually, you have to find out the jet become more effective?
Yeah, actually, very good question. So, depending on where we're at, from the ground all the way up to 300,000 feet, we can successfully abort. So, if it's just after launch, we're not going to be that far from the ground, so we're not going to fly that high. Just like if you fly off of the pad, you're only going to go about a mile high. If it's early in the flight, we're going to move as quickly away from the vehicle as we can, but still it might not be that far. So, for instance, if we were launching and we were a mile above the Earth's surface, we would probably at that point fly another mile or two away from it.
Yeah, that's another thing that makes this such a challenging analysis problem, is you have to be able, you don't have a definite starting condition. You know, it could be somewhere along a trajectory, but you have to analyze a trajectory all the way up because you could abort at any point along that trajectory.
Yes?
What controls the orbit?
What controls the orbit?
Controls the orbit. Well, the trajectory gets us up into an orbit. You know, the launch vehicle gets us up into orbit, and then to deorbit, I believe there's, you know, a deorbiting burn.
But you showed a picture of one where you changed the orbit.
Oh, yeah, okay, I'm sorry, thank you. Now I understand your question. Yeah, so you noticed in that animation of that launch that there was a rocket engine on the end of the vehicle. That's what the industry refers to as the Delta IV kick stage. It's the upper stage of the Delta IV vehicle. And that stage and that rocket motor are what are used to change the orbit. So we ballistically enter into an orbit around the Earth, that just an elliptical orbit, and then by igniting that motor, we can actually accelerate ourselves out to a higher orbit. Actually, we go out to 3,600 miles before we turn around. And as I mentioned, we don't use all the fuel getting out to 3,600 miles. We actually keep some of the fuel and turn it on and actually accelerate the vehicle back in when we're coming back. So, yes. Yes, sir.
Can you tell us something about the models you have up here?
Yeah, John, you want to?
Oh, okay.
I'll let John be my Vanna White.
Okay. So start here with the model of the, the model of the SLS. So as Kevin said, the full-scale vehicle is about 321 feet.
I think that's 1/200.
1/200, so 200 times bigger than that. So all of this is said is the space launch system, the new rocket that's being developed to take us beyond low Earth orbit. The little part on top, which we think is the most important part, is the Orion, where the crew rides.
Yeah.
Of course, launch aboard, the crew module's in there, and service module. So we got a smaller model here just of this upper part. So there would be the launch abort system, crew module.
Yeah, just as John said, we think this is the most important part of the vehicle. We definitely want to take it off and carry it with us. So this is that kick stage that I was referring to earlier. This is actually the upper stage that allows us to accelerate into higher orbits.
And Kevin showed the different parts, service module. Now this is an earlier design of the solar panels. Now we're going to we're partnering with the Europeans for a service module, and the design now is more rectangular looking solar panels, so that's earlier design, but crew module and launch abort, and just a larger scale so you can see it, same thing of the crew module, of course, be in there like that, flying when you do an abort, and after you do your reorientation, that jettisons and the crew module.
That's what telescopes to 10 feet?
Sorry,
Yeah, it doesn't. It actually compacts. Compacts. Yeah, when you hit the water, our simulations indicate that 30-foot long tower actually is compacted and down into a space that's about 6 feet. When we flew Pad Abort 1, and it's just a little bit of interesting trivia, we flew Pad Abort 1, and the tower, as you saw it streaking down to the ground whenever the crew module was so beautifully floating to the surface under the parachutes, we decided to get there a lot faster. Our jettison motor actually ended up in the manifold of the abort motor whenever we pulled everything out of the ground. And the whole vehicle was about 20 feet in the ground, I think. It just burrowed itself right down in the ground. But yeah, we actually put the entire, and I want to make sure you understand, the entire jettison motor was compressed and shoved into the little manifold, which is where the nozzles are on the abort motor.
jettison motor right there.
So that entire structure was compressed and stuffed inside that little manifold from the impact. So, yes, ma'am.
Is the Orion that's in the Air and Space Museum, is that just the mock-up, or is it?
Actually, you just saw that vehicle fly. That's the one that flew.
That's what I wanted to know.
And it was, that vehicle was designed and fabricated by NASA Langley Research Center. We're very proud of it. So, but yeah, you can go see that. And it's interesting, too, to see that because it is full scale. We've made a few changes since then. The cone, the back cone, actually, we've changed that to make it a little bit wider at the top. We did that because we realized we needed bigger parachutes after we did Pad Abort 1 flight test. So it's just a little slightly different, the production vehicle.
Bigger window in so people can look in.
Yeah. Yeah, yeah.
Quite a few of the people in this room were living here when Virginia did not vote for a certain person for president. And that new president moved NASA, a lot of it, from Langley to another state. If you were familiar with it, you were too young to probably.
Well,
I'm glad to know
you're not talking about the president I thought you were.
doing fine.
So yes, we are actually doing fine. I've read a lot of the history of NACA and NASA and that whole activity, and it's very, very interesting. That team of people who left this area and went to Texas were a very interesting group of people. They were young, they were excited, and they were willing to take risk, and they did that very thing. And so they were willing to go boldly forward. And we're glad that they were there leading us at that time, quite frankly. But we didn't, Langley wasn't left in the lurch at all. And we are very excited to be, I think, at the epicenter of activities on developing the new vehicle. So, thank you. Yes?
Is any thought given to a dry landing as opposed to ocean?
Yes. Actually, that's an excellent question. And you know, when John and I were putting this pitch together, we actually thought about putting a chart in to kind of describe why we didn't do that. When we initially started this program in 2005, we wanted to land anywhere. Please don't take that literally. We wanted to land in the water and on land, and which does significantly expand our operational capabilities. But what we learned was the system to land on the land cost us about 600 or 700 pounds of mass. That's 600 or 700 pounds of mass that we would have to carry with us to the moon, to the asteroid, eventually to Mars, and it just was too costly to do that. So we had to get rid of that system and rely on the water landing system, which is a much more mass-efficient system that we can use. Now, you'll notice, as John said, the commercial guys are only going to low Earth orbit, and some of them are actually proposing systems that will land on the land. And the reason we can't do that is because you just can't carry that much weight with you whenever you're going so far away. Another differentiation or question that might come up is, why do we have a tower that's pulling us off the vehicle? Why don't we just use the service module? It's a giant motor. Why don't we just go ahead and use it for all of the aborts? Because as John said, when we get above 300,000 feet, we can use the service module to abort to orbit for a rapid reentry. And the reason is our service module for the Orion weighs about 36,000 pounds. We need that large vehicle with all of the fuel that it carries with it in order to explore to the moon and beyond. It's just a matter of physics. We just need that much propellant to take with us so we can get back, get out there and get back. Whereas if you're going to low Earth orbit, an equivalent service module system would only be about 12,000 pounds. So it's about 20,000 pounds lighter. So when you talk about getting away from a launch vehicle, which we have to do very quickly, if you're trying to push yourself and a 36,000 pound motor off, it's just not practical. So we had to go with a tower system on top so that we could manageably remove the crew module over that full flight regime successfully. So, thank you.
Thanks to John for giving us the opportunity to present to you today. And next week, next Thursday, we're going to be talking to the Space Launch System guys, the folks that actually built the launch vehicle. And they may have a different story. They may say this is the most important part of it. So we're going to see how it plays out. So you be the judge next week, okay? Thank you very much.